Yes, because today there is one international student attending the class and speak English. Uh, so today the first lecture of, for the review on algebra, and I said this big picture of algebra because I will try to explain algebra in the geometric way, so you can imagine the picture of algebra. When you see a matrix, you can see a picture of it, and you can see space and how you can manipulate the space geometry. So you will know very clearly what matrix is, what algebra is, and the organization of my lecture is in this way. I will try to pick up some very important points and related to each other, one and another. And until can provide application that you can understand the application based on the knowledge that you have from here. So one lecture must reach one application. For instance, here I will try to reach application in a control system, especially for multi-input, multi-output, multi-input, multi-output. So next lecture, I will try to work on other application, for example, optimization. Okay, so I think yeah, you already have this list. I can erase it and just leave one. So first, it's about row and column picture. So what does it mean? What you have learned before is that, for example, you have one matrix like this, and multiply by a vector, say like this. Then you do the multiplication in the algebraic way. So you have like 3 times 1 plus 1 times 2, and here you have 3 times 1 minus 1 times 1. So in this way, you do not know, you don't see the picture of it. If you just multiply it by it like this. For example, you have you are requested to solve equation. Let's call it A, matrix A times vector H and equal vector B. For example, A is 1, 1, 2 minus 1, and here let's say it's H1, H2, and B here, let's say I don't know this, and I know B. So 3 plus 2 is 5. 3 minus 1 is 2. So let's say you are asked to solve this equation or to see the picture of this equation. Yeah, you can solve it directly, but today, not just to solve it, but I want you to understand the pictures. So what can you see the picture from here? First, about the row picture. So what does the row picture look like? So first, you multiply it, you have h1 plus 2h2 equal 5, and then h1 minus h2 equal 2. So what you can see here, there are 2 variables. So in the graph, geographical representation, you can see this is a line. Let's say if I choose h1 and h2 as Cartesian coordinate in a dimensional space. So for this one, you got one equation, and this one you have another line. For example, like this. So it means the row picture. So you see the row. This is the row. The row pictures mean you are trying to find the intersection of these 2 lines. So you got h1, which is the root, and h2, and h2 the root. So this is called row picture. Row picture is intersection between two geographic representation, which is line, two lines. If you have three variables, let's say you have h1 plus h2 plus h3, 2h3 equal to something, let's say 8. There's a 2, 2, 2, 4, 6, 8. So h1 minus h2 minus h3. So 4 minus 4 equals 0. Let's say all equal to. And then we have h1 minus h2 plus h3. And you have 2. For example, like this. And the row picture of these three equations are 1. So this represents one plane. Let's say at the let's say one plane like it's a little bit hard to draw it. You can imagine at the corner and a room. So you have three planes intersect. One is the floor, the second one is the side, and the third one is the side. So you get all the three intersect with this at the corner of the room. So this is the row picture. Row picture means you try to intersect some geographic some geometry and to get the solution. In the similar way, you have three planes intersecting in three-dimensional space. You will get the intersection with this point. So you get the root, h1, h2, and h3. So this is raw picture. Now let's see the color picture. Color picture of this equation. Back to this one. So for the first part, when multiply. Now I don't multiply this way. I don't multiply this way. I multiply this way. Choose like this. So h1 multiplied to this column meter, h2 multiplied to this column meter. So a matrix, you got a matrix A equal to 1, 1, 2, minus 1. But now you don't call it a matrix, you call it another way. You call it, this is the first column A1, and this is the second column A2. Maybe small case A is better. A1, A2. So when you multiply it by h, you got h1 here, h2 here. You multiply this way. h1 times kilometer A1, and plus, so this is kilometer, plus, yeah, I call it you know, like this, we value this is kilometer, and then you got here h2 times A2. So this is called linear combination between two vectors. So let's say if I draw one with the A1 in 2 dimensions, so no space, but here it's not equal to 2. No confuse. Let's say I have a space with 2 dimensions. 2 dimensions because I got the dimension of A is 2, 1, 2. So let's draw A1. Let's say A1 is here. This is A1, and A2 is A2 is 2 minus 1. Yeah, so this is you need 1, 1, 1, and then you need 2, 1, maybe like 2 minus 1, something like it. Yeah, I try to draw it. That can represent this one directly. So 2 unit from here and minus 1 is here. So it's supposed to be here. This is A2. So the color picture means that if you want to solve this equation, A is equal to 3. So you find 2. It means how you find h1 multiplied to A1 multiply to A1. So let's say, yeah, this is H1 times A1. And then H2, you got H2 times A2. Let's say up to here, I don't know yet. H2, A2. And then you add this together. You add this together, you got vector B. This is B. Okay, B here. This is so column vector means you do the linear combination between all the vector in all the column vector in the matrix A, and you try to find the coefficient that when you do the linear combination, then you get the result of the right hand side, which is B. So try to imagine. This is very, very important. The most important basic concept for the linear algebra column vector. So when you see A times 6, you can imagine that that is the combination between the all column vector. See? Linear combination of this vector will result just a vector, and you want that vector equal to the right hand side, so that you get the right answer of H1, the coefficient H1, H2, and so on. Something like that. So in our case, you got 5 and 2, maybe. So you got B. Actually, you got B first. If we want to solve this equation, so you got a 5 unit on here. So this is 2 unit, 2, 3, 4, 5, or 5 times in here, and then you got I should, yeah, 5 and 2. So here should be 1, 2. Yeah, 1, 2. So I should have. So this is B. Actually, this is B. So that how you find H1? So to find H1, you this is B, right? So yeah, so I draw this is just B first. How you get how you must find H1 and H2 so that these two linear combination equal to B. So what can you do with this? First, draw this one parallel to this one, okay, for the geographic, and you draw this parallel to this one, like this. So you must find H1 so that H1 times A1 reach here. Maybe my drawing is not good. Actually, this one should also be here. Yes, so this is just a drawing. You need to carefully make the right unit. Okay. So now you got a picture of row and column. My next point is about square matrix, and inside the square matrix, we talk about linear independent. Okay, so next is linear independent. Linearly independent. Linearly independent. This should be inside a square matrix. Yeah, I call square matrix first. Okay. So now you got some keywords, linear combination, and next you get linear independent, linearly independent vectors. let's say I will talk about three-dimensional vector. Oh, okay. Let's say just two vector first. Right. Okay. Let's say I have this vector A1, vector A2. If I use this is zero, because I want to talk about three-dimensional vector. Then, if I put here phi and 2, let's say phi 2, and let's say okay. Now I have a matrix A. Let's call A equal to this. So can you make some combination of this vector, and then you get this vector? Let's say I how can I say? Okay. I should say that let's say if I want to find alpha 1 times 1, 1, 5 plus alpha 2 times 2 minus 1, 5, and alpha 3 times 5, 2, 0, 0. Can you find alpha 1, alpha 2, alpha 3 so that you can add this? You do this linear combination and get 0. You remember before that you have this. If you multiply this vector by 3, let's say if I use 3 here, and I use 1 here, and then I use 0 here. Oh. Yeah, let me change it a bit, make a smaller, yes, and 0. Okay, so I choose this one is minus 1, and then I choose here is 3, and then I choose here 1. So I got this 2, 0. Okay, like this. Equals 0 now. Three. Oh, here's minus 1. Okay. 3, 5, minus 5, 0. 3, minus 1 equal 2, 2 minus 2, 0. And here, minus 3 plus 3 minus 0. So it means you can do the linear combination between this and this, you got this. So what does the column picture looks like? Now you have three dimensions, but now you have 3 vector. You got 1 vector here, and then you got another vector here. But you can do the combination. You can do the combination of these 2 vectors to get this vector, right? So you got here is now I call this A1, A2, A3. Okay. So you can find 3A1 and plus A2, 1A2, and you 1A3, A3. So you add this and this equal this, or add this, and minus this equals 0. Same thing, right? So it means like this. So if I move this one to the right hand side, it will equal like this, and here it becomes 5, 2, 0. This is what I mean here. So you take this and add this equal to this. So it means you can combine following the linear combination property and get the other vector here. So we say all the column vector here are linearly dependent. Because you can combine these two equal to this. So imagine the picture of three-dimensional space, and you have three vectors. So what picture can have? I draw a more convenient way to visualize it. Let's say you have vector on this plane, and then you have vector on this plane. When you make combination, then you still got another vector in this plane. Okay. So this is one picture. This one also. All the three vectors, you can say all the three vectors stay in the same plane. You got it? Stay on the same plane. See? Stay on the same plane. So if three vectors stay on the same plane, can it produce a volume? Can the three produce a volume? Yeah. Can only produce surface, but cannot produce volume. So if you have three vectors, let's say you got two vectors in here. You got two vectors in here, but another vector is like this. For example, if A equal to let's say 1, 1, I give it 0. And then 2 minus 1 is 0. But this one is 5, 2, 1, like this. So these two stay in the plane. Let's say plane dimensional 1, dimension 2, dimension 3. Okay? So these two stay in plane by axis 1 and axis 2. Because they do not have the third component. But for the other vector here, this one, A3, let's say A3, it has all the three components. So it means point out of the plane. So can these three vectors produce a volume? Yes. Yes. And can you do the linear combination of these two and get this one? No, right? It's not possible. If you combine these two, no matter what you multiply this by a number, multiply this by another number, when you add up, it just becomes still 0. It means it always stays on this plane. So never you can get these two combination of these two to get this. And also you can get the combination of these two become this, never. But for this, if you can do combination of these two equal to this one, you can also make combination of these two to get this, always. Just if columns are dependent, rows are also dependent, always. So this is one more property you just learn, okay? So this is interesting. So this one can produce volume. So what volume has to do with some property of algebra of a matrix A. So in this case, when you find determinant, because my next point is after linear independent, range of matrix. Okay, let's call range. So Let's call range first before determinant. So this one and this one are dependent or not, these two. Can you multiply something on this one and make this? Just multiply number to this vector and get this vector. Can you? You multiply by -1, you get this -1, but you cannot get 3. What I'm doing it. So I want to check whether this independent from this or not. So of course, this independent from this because we have this one and this one very different, right? In the direction. So here. So these two are independent, but these two can be combined to make this one. So it means this one is dependent on the other two. So in here, I can say that among these 3 column vectors, there are only 2 independent vectors. Only 2 independent, 2 linearly independent. So it means the rank of this matrix is 2. Okay, so there are 2 linear independent. But listen, if we write this as a noun, we can use linear independent vector. Only 2, which means rank of A in this case equal 2. What if I have this other matrix B? If I have another matrix B like this, if I have another matrix B like this, B equal to 1, 1 minus 1, and then 2, 2 minus 2, and then combination of these, I got, let's say, yes, multiply 2 here, let's say 4 minus 4. So now my question is, does this vector independent from this? Independent? Yes, dependent. If I multiply it by 2, it is the same as this. See? Just multiply 2, come 2, minus 2. How about this one? This vector is independent from these 2? No. This one also dependent. Whether you combine these 2, multiply 2 here, multiply 1 here, and you sum up, you can get this. Or you just multiply 4 to this parameter. Get this. Or you just multiply by this vector by 2. So it means in this matrix there is only 1 independent vector. There is only 1 independent. But for matrix, at least it has 1 independent vector. Except all the entries are 0, then it has 0 independent vector. Okay? So independent vector. So it means the rank of B, this B, not all the B, but just this B, equal 1 only. Okay. Let's see the connection between rank and determinant. Yes, my next point is determinant. I don't need to erase. So determinant of a vector or of a matrix represent the volume. You try to find, there is a proof that if you use the we call what products หมายเลขขอบคุณรอบขอบคุณรอบนะครับเป็นเอกสารเลย yeah, if you try, let's say you have A1, A2, and A3, and then you use A1 cross A2, and then scalar with A3, yeah, become a volume. And this volume is just determinant of A. Okay. Because this cross this, the magnitude is the surface of A. Why is surface? Because A cross A1 cross A2 equal to magnitudes A1 times magnitude A2 and times the sine of the angle between the two. Then is the formula of surface. Okay, the magnitude is the surface, and when you multiply by A3, you multiply the magnitude of the surface with magnitude A3 and times cosine between A3 and the plane, and then it becomes volume. That is the proof. You check by yourself. Today you just remember that determinant of a matrix in 2 dimensions or in 3 dimensions, the geometry of determinant is volume. 4 dimensions also volume, but volume in 4 dimensions. Okay. Okay. See the connection between range and determinant. Okay. Let's see. For this one, it has 3 dimensions. This let you say, but it only has a range 2. Okay. And we see that the vector are linear dependent, so it only forms a surface. Yeah, real inform a real. So determinant is volume. So if you only have surface, it means the volume is 0. Okay. So if the range is not full, this keyword, if the range is not full, use 3 dimensions, but you have only range 2, means determinant is 0. In this case, range just 1, of course not full. Then the volume is, it does not even have surface, it don't have line. Because this is one vector, and this is just a vector on the same direction, the scale up. This one also on the same. It cannot even form a ring, only a line. Let alone a volume. So it cannot form a volume. So the determinant of V is also 0. But this one, let's see this one. See this one. All the 3 vectors are linearly independent. Okay? All the 3 vectors are linear independent. Okay. So it means range equal to range of, should call it A1. Range of A1 equal to 3, full range. Because dimension of A is 3. Dimension of a vector, you can say, dimension of each column vector is 3. And these 3 vectors form a full range. Okay. Then determinant of A1 here is not 0, different from 0. In this case, determinant of V is equal to 0. In this case, determinant of A equal to 0. Okay. So there are many keywords and properties you must remember. First, row pictures, column picture, which is combination of vectors. Okay. A times A means just linear combination of all column vectors. Okay. And now you got the property of linear dependent and independent. So if all parameters are linear independent, then it has full rank, and that one has full rank, then determinant is not zero because it can form a volume. Just remember this picture. And if the kilometers are linear dependent, then those vectors cannot form volume. The determinant must be zero. Okay. Can you have the picture in your mind? So when we ask something, you can imagine the vector form in this plane, or if dependent, if they are all independent, they stay on the same plane, something like that. But if one of them or two stay on the same plane, but the other one is not stay on the same plane, then it can form a volume, then it has full rank, and then determinant is not zero. Easy to remember. So let me show you the equation of A equals 0. This is important because you will use it for finding eigenvalue. So I keep this, and I still keep this. Okay. Now let me analyze on Ax equals 0. For example, if you are asked to solve Ax equals 0, so you already remember that when you multiply x into A, so x1, x2, x3, multiply here, so x1 times this, x2 times this, x3 times this, and then you sum up, and you 1 equal to 0. It's like this, right? Like this. So it means, can you find x? Yes. X must be 3, 1, minus 1, right? Correct? So what does it mean? It means if kilometer of A are dependent, then you can find X. You can find the solution A from equation Ax equals 0. How about this case? I mean, you can find H which is not 0. Of course, if you choose it 0, when you multiply it, you can get 0, right? Okay. But it's not interesting, right? Okay. Now we want to know whether you can find H which is not 0, and you can solve this equation. I mean, the solution H for this equation, solution H which is not 0 for this equation. How about this case? If I want to solve A1 x equal to 0. If you find x that is not 0 and satisfy this equation, because we always know that you cannot find a combination between these two vectors and make this vector, right? Combination of these two to get this. So of course you cannot make combination of all the three to become 0, right? So this one, the solution only n equal to 0. Okay. Now you see the property, the nice property again, the nice property that if determinant of A is not 0, then we can find inverse. If determinant is not 0, okay. Because of this, we can find A inverse. So I mean, A inverse exists for this one. A inverse exists. If A inverse exists, we just multiply like this. Then you get what? Like equal to 0. That is a unique solution. But in this case, can we find inverse? No, A inverse does not exist. A inverse does not exist. So you cannot just multiply by A inverse for both from the left hand side to both sides. And the nice thing is that we can find H which is non-zero that satisfies this equation. So I said this is very important because you are going to use this property to find eigenvalue. Okay? Find eigenvalue. Rank, determinant, and then reduce row echelon form. So before finding eigenvalue, I want to show the reduced row echelon form. So what is it? What is reduced row echelon form? So I can erase this. Reduce row echelon form. So it's straightforward. Reduce row. It means you try to eliminate the row to have all 0 except the diagonal. Okay. Okay. So let's say you try to eliminate this. It means you, okay, let's say reduce row echelons form of A equal. I think this is the final result, but first we use Gaussian elimination. Gaussian elimination. First we eliminate this one, so you keep 1, 2, 5, multiply by -1, and add up, so you get this one 0, and this one 3, and this one 3, -1, and add up 2, right? 3. Okay, it's 3. And this one, you just add up, you get 0, 5, and then 5. Aha. The security is too dependent. I already told you before that if kilometer are dependent, kilometer are also dependent. So you eliminate again this first, then second Gaussian elimination. You can make, yeah, this one still the same, and this one you can keep it also, and this one multiply by -5/3 and add to this, you will get 0, 0, 0. Okay. And then you try to eliminate the eliminate what? Can you look? Yeah, make this become 1, 1 first. Okay. The next step, make this become 1, 1, and the next step, try to eliminate this one, become 0. Okay. So the this one can be different number. Okay. I see this one is still 1, but this one is something else. So finally, you got identity here. So reduced row echelon form is the way to have identity matrix according to the rank. If it has two rank, you will get identity matrix with two dimensions. If you have three rank, you get all. But if you have only one rank, then you get only one here and all zero. Okay, this is echelon form. Okay, it's very nice property for you to solve rectangular equation. No, I mean AX equal B, but A is rectangular matrix that have the number of columns larger than number of rows. So we need this reduced row echelon form. But today I will not cover it. So okay, the next part will be very important, which is to find eigenvalue and eigenvector. Okay. So H is here. So it means you can find H. So I will not delete this. I will not erase this. So I will erase this one. Echelon form is not very important for today. Eigenvalue by definition. Okay, so first definition. Eigenvalue and eigenvector. Okay, definition. Definitions is like this. You have a matrix A, and when you find a vector X, and then you just scale the vector X. So lambda is scalar. Is scalar, and it's called eigenvalue. Okay, to avoid the same notation, let me use U. So you have vector U and value lambda. When you multiply U by A, then you just scale U by lambda. And U is called eigenvector. Okay. So this is definition. How you find eigenvalue lambda and eigenvector? So this is how you find it. First, move lambda U to the left hand side, and then you get 0. Then take a U as a factor here, U is here. Then here you have what? Have A minus, but lambda is scalar, you cannot subtract lambda from A. So you need identity here for 0. Now you have AX equals 0. AX equals 0. Can you find U? Can you find not 0 U so that you have this matrix and U equals 0? It's just like this. Can you find this H? Okay. Okay. So, and then yes, you can find if A is not full rank. If A is not full rank, right? The determinant of A equals 0. So from here we got determinant of A minus lambda I equals 0. And then we do the process of determinant. Let's say 3 by 3. If 3 by 3, you know how to find determinant. Yeah. Pick 1 and multiply it by its cofactor. And 1 multiplied by its cofactor. Yes. So just do the process of finding a determinant here. So you have equation. You will get equation for polynomial. polynomial of lambda equals 0. If A is 3-dimensional, you will get 3-degree polynomial. Yeah. So if A belongs to R n by n, then you will get polynomial dimension n of lambda. So if you have polynomial dimension n, then you can find root. You can find n root of lambda, and those roots can be real or can be complex. Yes, by degree n is mean root n. Dân như là lô mean n mean root complex. So after you find lambda from here, and then substitute back to here in order to find u, because you have system equation. But in the process, I can let you know now that in the process, when you find it, you will get the infinite solution of u. Infinite solution of u. So you, but the direction of u, infinite solution in the sense that if one vector or this vector u can be short or long, right? You just see here. If I substitute u by 2u, here I substitute 2u by 2u here, you still get this equation satisfied, still, right? So it means the solution of u is not unique. It's not unique in terms of direction, but the direction unique. Direction is unique, but the length is not unique. So usually in the application in computer, we select u so that the length is 1. If you select 1, then you get just like you have a unique solution, but it is not. Okay. So this is the connection between linearly independent, linearly dependent with the way you can find eigenvalue and eigenvector. So I only show definition and only show the process, but I will not give example on the process to find these values. I assume that you can find solution from polynomial, but higher than degree 3, maybe you don't know the way to find. Computer can. Don't need to worry. Okay, but the most important part for eigenvalue is that how you apply this eigenvalue in the field of engineering. Yes, this is very important. Now you just know the concept how to derive this. Okay, so next would be eigenvalue decomposition. So there are many features and keywords and ideas and concepts in here. I think it's not easy for you to remember just by attending this one lecture, because there is a video record you can see here, and you try to imagine by yourself. Imagine all those vectors, all those features. PM สมัยថារូបភាពវាមិនទេមិនហ្នឹងបានចាំបានយូរតែមិនយ៉ាងទេថតតែច្រើនយ៉ាងហ្នឹងស្អែកឡើងស្អែកអាចទៅចាំដល់វាស្អែកខាងស្អែកគេសួរទៅទេឬទៅខ្លះពេលមកទឹកក្រោយគេសួរវិញទៅដល់ពី3ហើយបាទមិនខែហើយអស់លីទៅដល់លីហើយអាហ្នឹងចឹងសារមើលចាំ picture វាល្អហ្នឹងចាំជាប់ល្អណាស់ចាំតែមិនចំណុចទៀតដាក់វាមិន the next point, this point, oops, okay. This point is about eigenvalue decomposition. Decomposition. So I want to, because from here, okay, From here we have unsolution, right? Unsolution of this equation. It means we have unsolution means we have lambda 1, lambda 2 until lambda n. Okay. So if we have all the lambda, then I can rewrite this one as AU1 equal to lambda 1 U1. So each lambda we also have eigenvector corresponding to this eigenvalue. Oh, by the way, I only focus on full range matrix A. I forgot to put here just to make my lecture more accurate. I add here for full range matrix A. For the not full range matrix, I will cover in a later lecture. And then I also have AU2 equal to lambda 2U2. Then AUN equal to lambda n. So these are kilometer. These are kilometer, right? So now I put all kilometers together to make a big matrix. Actually not very big, just n-dimensional, just like A. Because A is n by n, but when it multiplied by a vector, it becomes a vector, right? So this is n by n, this is n by 1, right? So when you multiply it together, it's just n by 1, which is a vector, right? So now I put it together. I have AU1, then AU2, then AU, and this. And I have lambda 1 U1, lambda 2 U2, lambda n U1. Then what can I do with this? This is A. I can take A as a vector for me. So A, and then it is U1, 2. And then here, now I want U1, U2, U1. So what can I have in front? Kilometer. You can multiply. If you kilometer, lambda 1 times it, lambda 1 times this also. Lambda 1 times it. We have what? We have what? Have. Okay. So, like this. This is row. Lambda 1 multiply. Yeah, like this. Oh, I think this is wrong. I think this should be on this side. So, like this. I got 1, 2, 1, and then lambda 1, lambda 2. Diagonal matrix. So can do like this, and like this. So lambda 1 vector of U1, and then the second column like this. The second column will lambda 2 will multiply by U2. So here I can write out A U capital U equal to U times lambda. Lambda is diagonal and Finally, eigenvalue decomposition is A equal to lambda. Okay. Lambda is diagonal. U is the matrix of all kilometer of eigenvector. Okay. So you got all eigenvector and put together like this. So you have a matrix of eigenvector, and you put all the eigenvalue as a diagonal matrix, then you get this diagonal matrix lambda. So how can this be used with control system? It is easy to use this for solving system of linear differential equation. So we can see the application right now. I can you can see. So I must read the application, and why you will feel that this is very boring. So, okay, next is solution of linear differential equation. Of system of linear differential equation. Okay. Solution of system of linear differential equation. Let's say I have equation x of x dot x1 dot let me choose Okay. But, okay, so x1 equal to minus 3x1 plus 1x2. X2 dot equal to minus x1 minus 3x2. Okay. And x1 of 0 equal to 2, x2 of 0 equal to 1, for example. So for this, we can write equation as h1 dot h2 dot equal to here matrix A minus 3, 1, minus 1, minus 3. X1, x2. Okay. So if you want to solve this equation, it's not easy because this equation there are two variables. It's 1 and it's 2. What if we can separate? We can have a way to separate that. Equation 1 has only one variable. Equation 2 has only also one variable. You can do that. It's easy to solve. Yeah. Let's say if you have y1 dot equal to let's say minus 2y1. Can you solve this equation? It's very easy. Yeah? So that's why here we use the eigen problem. So how? Let's let this matrix A. So if I substitute A by U inverse times lambda and U times lambda and U inverse times A. So here is this dot equal to like this. Then what can I do with this? Now I multiply by U inverse. U inverse is dot here equal U multiplied by U inverse combine this. So now I have lambda U inverse H. So let y equal to U inverse times H. Then what you have y dot equal to U inverse, because U inverse just number times H dot. So here you have y dot equal to lambda y. Because lambda is diagonal, what happened? Or lambda 1 dot lambda 2 dot because y1 dot y2 dot because lambda is diagonal. When you multiply, you only have lambda 1 y1, lambda 2 y2. So can you solve this easily? Yes. So it means you can have y1 dot equal to c e to the lambda t, lambda 1t plus c1, okay? And y2 will be c2e to the lambda 2t. It's easy to solve. For this problem, you can find lambda 1, for example, equal to -2, lambda 2 equal to -4, then you can have this. Okay. And what is C1, C2 can be found from this condition. So first, substitute y by what? Actually, I can say or in here, or if you want to find h, which is just you multiply by y. Okay. So you want to get x instead of y, make it as a vector, and then multiply u from the left hand side, you can get x. You just number, don't worry. Number. And C1, C2 still parameter, but you can find them from these two equations. So I only explain the process, and you do exercise by yourself. It's better. It's better to get familiar with it, so you can remember. So this is the application for solving a system of linear differential equation. So what does it have to do with control system? What does it have to do with control system? So in control system, in physics, all physical systems can be derived in the form of differential equation. And for controller design, you can linearize the system. So when you linearize the system, you will get a system of linear differential equations like this in control system. Control system, you have this form. So you have state X and you have input U. So to check whether the system is stable or not, you just check eigenvalue of A. Why? Because here you can see that the solution related to the exponential of lambda t. So what is lambda is positive? Okay. Let's say it is error. Let's say for one system, for example, if it is a DC motor and you want to control velocity, then it is the error of the actual velocity and the command velocity. Just example. Or a pendulum, or you have a pendulum. You want to control. Maybe I think it's better to say, yeah, just DC motor is better. So if it is error between X is error of actual velocity and position of a vehicle whatever a vehicle, maybe of a vehicle. Actual velocity and position of a vehicle tracking a plane trajectory which means it's actually just error of let's say velocity. Okay, let's say position should be okay. Position desired minus actual position and velocity desired minus actual velocity, for example, for vehicle. So this equation represents the control system after modeling from the physics. And so what we want to have is to get x asymptotically go to 0. Because we get error go to 0. So in many models, we want that. Want error go to 0. So in here, if you from this equation, if you still remember, there are particular solution and homogeneous solution. For homogeneous solution, we only care here. Okay, for homogeneous solution. Homogeneous solution. You only care here. We mean just like this one, just like here. Yeah, this is not equal to AX. Okay. So when you solve, you get x1, y1, y2 equal to here. When you use eigenvalue, you position to solve equation, you get x equal to u times times C1 power lambda 1t is C2 e power lambda 2t. Okay, you have this. The use have y is x. So if you want x go to 0 when t go to infinity, if you want we want x of t go to infinity go to 0. We want that. So it means lambda 1 and lambda 2 must be negative. So if lambda equal to 0, it means you get the constant at some point, not grow, not decay. So it's okay, still stable. Okay. But most of the case, if it's stable, it means if it's not go to 0, it means the error is not 0, it's not polygon, right? So it should be strictly less than 0. So that's why when you see a control system is not equal to AX, and you want to know whether this equation is stable or not, you just check the eigenvalue of A. So this is just to check this system only. What if you want to control to design a controller? So when you design a controller, you choose U equal to, let's say you choose to control. You choose U equal to Kx, for example. Let's see this case. Okay, let's see this case. In this case, you get h dot equal to ax plus b k, and this should be minus. Okay, so minus bk h. Then you have a minus bk. So in this case, if you want, we want for this one, sometimes we want, but we cannot get that because it depends on the nature of system. Because without control, right? In this case, we want it, but sometimes we cannot get it. But in here, now you can control it. You choose k. So here you want h of t go to infinity. For t go to infinity, you want h which is error go to 0. So now you can choose k. You can choose k such that eigenvalue of a minus bk or negative. This is the point for control system. So here you apply eigenvalue for control system. So long story is from very basic algebra, row picture, column picture, especially column picture, and linear combination, linear dependent, and then definition of eigenvalue, and then you apply eigenvalue for solving a system of differential equation, and then when you want to control, you want to get a stable system, you want an error which is the state of equation to go to 0 when t go to negative, and then how you choose k such that lambda must be on lambda of this matrix must be on negative. Okay. So in order to understand very clearly on this topic, you must remember all the points I just mentioned. Yeah, so lecture today end here. So you can stop the record. But trong miền núi còn là bài mỏng và mỏng vào bài mà giờ mình suối này giảm cao ôi máy nó record được gì record này chồng như record chồng cái điểm poly play này record này ăn vô luôn đấy poly máy này record đấy bạn còn đấy chụp này bật nó